Alright, so this is going to be a fairly quick video, but I'm just going to go over lesson number 3. I'll start from the beginning, and I'll cover what we didn't go over in class. So let's look at this first example again. So in 2012, the university population of the country was 160,000 and was increasing at an annual rate of 4.5%. First question is we want to know what the values for A and B are. Well, A is going to be our initial population, and that is 160,000. And B, if we're putting in the form of y is equal to ab to the power of x, then b is our rate of change, and we know that our rate of change is increasing annually by 4.5%, and so that is going to become 1.045. What we do is we turn this percentage into a decimal and add it to 1, which is 100%. All right, now what we want to do is write the equation to represent how this population changes as a function of years. And so what this is going to look like is, if we're looking for the population, then P is going to equal 160,000 times 1.045 to the power of n. And we want to determine the population in 2015. So if we're looking for the population in 2015 and our current year is 2012, then that's going to be 3 years later, which means n would equal 3. Because we go 2015, subtract 2012, and we're left with 3. When we type this into our calculator, we're going to get a number of 182,587, which I rounded upwards. Now let's look at part D. If the population continues to grow at this rate, so 1.045, determine the number of years to the nearest year for the population to double from its 2012 size. All right, well, let's make a list of what we have. We know that we're looking for our population when it doubles, so if I were to double 160,000, I'm going to be left with 320,000. I have my initial number, or my initial population, which is 160,000. I also have my rate of change, which I'll call my B value, and that was 1.045. But now I don't have my number, the number of years it's going to take for this population to double in size, so I'm going to be left with n. Now let's set up what we have. We're going to have 320,000. If I plug it into this formula, 320,000 is equal to 160,000 times 1.045 to the power of n. If I divide both sides by 160,000, I'm going to be left with 2, because 160,000 goes into 320,000 2 times. And I still have my unknown on this side, which is n. Now what we have to do is turn this into a logarithmic equation, and so in log form, I'm going to have log of 1.045 2 is equal to n. And if I change the bases, change the base identity, then I'm going to be left with log 2 divided by log 1.045. And I'm going to need an answer of 15.747. And we're just going to round that up to 16. So it will take 16 years for the population to double. All right, let's move on to the next examples. Now what we're looking at is an example where our population is decreasing. So the number of fish in a lake is decreasing by 5% each year as a result of overfishing. If the number of fish present in an exponential function of time, state the base of the exponential function. So B, that's going to be my base in this case. I'm going to go 1 minus 0.05, and I'll be left with 0.95 as the base. Now we want to use write an equation to represent the number of fish after t years. Use n naught to represent the initial population, and n of t to represent the final population. So I have n of t, this is a function of time, and I know I'm starting with n naught, that's my initial population, multiplied by my change in population as percent, and as a function of time. Now, if there was 22,500 fish present in June 2012, how many would you expect to be present in June 27, so 5 years later? Well, let's determine what that would be. N of 5 is equal to 2,500 times 0.95. 2012, that's our year, and 2017, 5 years later, to the power of 5. And our answer is going to be 1934 fish. Now let's look at D. We want to know how long it's going to take to reduce to half the number. So if I started out with 2,500, I want to know what it's going to be when I have 1,250 fish left, because that is half of my initial number. And so what we're looking for is N, or sorry, not N, but T. We're looking for T, since it's our function of time. I'm going to divide 1250 by 2,500. I'm going to be left with 0.5 is equal to 0.95 T. If I convert this to logarithmic form, I'm going to be left with log of 0.95 0.5, and that is equal to T. And T is going to be equal to 13.51, or 13.5 years. Now this is I'm going to take a little slower through this next problem. This is the one we were looking at in class. But in this problem, we're looking at the intensity of a light, and of that light source when it's reduced to a certain value after passing through a certain distance of fog. Now we're going to use the formula I is equal to I naught E, which is our value used in our natural logarithms. Now let's see at what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value. So what we're looking for is D. But we don't have any, the only numbers we have is E and negative 0.12. So let's see what we actually want to determine. We want to know when it's 1/4 of its original value. Well, if IO is the original value, I want to know when I is going to be 1/4 of IO. So I know that in this example, I is going to be equal to 1/4 I naught. And so if I plug that into my equation, I'm going to be left with IO and 1/4 IO is equal to I naught E negative 0.12 D. What we want to do is divide everything by I naught, and those will all cancel out. And what we're left with is 1/4 is equal to E to the power of negative 0.12 D. Now, if I put this into logarithmic form, remember I'm working with my natural logarithms at this point. So this is going to become ln 0.25 and ln of E to the negative 0.12 D. Now, I didn't have to do this step. I could have put this into my ln immediately, which means that I'd be left with, let me point up here, I'd be left with ln 0.25 is equal to negative 0.12 D. And then what I want to do is divide both sides by negative 0.12 D, so I'm going to have natural logarithm of 0.25 divided by negative 0.12. That's equal to my distance. And we're going to get a value for our distance that is equal to 11.552, but we want it to the nearest hundredth. So we'll round that to 11.55 meters. All right, let's look at the last page here. We're going to look at half-lives. Now, this might be something you recall from chemistry or science 10. Radioactive substances decay by changing into non-radioactive substances. The amount of radioactive substance present at any time is an exponential function of time. And after a certain interval called the half-life of the radioactive substance, only half of the original amount is still radioactive. Now we put it into this form. A is equal to A naught times b to the power of t, where a is the amount that we started with, and t is the time that passes. And so we want to complete this the following to determine what the base in terms of the half-life is going to be. So when t is h, only half the substance will be radioactive, so A is going to equal 1/2 AO, which means that if A is equal to 1/2 of the initial quantity, then 1/2 AO is equal to AO times B to the power of H. And we want to solve for B in this case. So just like we did in the previous example, if we divide everything by A naught, these will all cancel out, and we're going to be left with 1/2 is equal to B to the power of H. Now, if I'm trying to get B by itself, I got to get rid of this exponent of H. And so right now what I have is something that I can make. What I have to ask myself is, what do I have to multiply H by in order to cancel it out? And just like in previous questions, if we put it over or under 1, that'll get rid of this, because 1 over H times H is just 1. Now what I'm going to be left with is B is equal to 1/2 to the power of 1 over H. Now let's look at what the next question is asking us. The exponential function is now in the form of A is equal to A naught times 1/2 to the power of 1H t, which can be written as A is equal to A naught times 1/2 to the power of t over H. Now let's look at the doubling time. The time is taken for an exponential function to double in value, and that's called the doubling time. The base in the formula for doubling time is 2 to the 1 over d, where d is the doubling time, and the exponential function is in the form A is equal to A naught times 2 to the power of 1 over d to the power of t. And we can rewrite that like this. Now use a procedure to the one above to develop this formula. Alright, well, if we're starting with A is equal to A naught B to the power of t, and I know that this is going to be double, so we're doubling A naught here, and that's B to the d. If I divide all of these by A naught, since that's what we're doing, we're doubling our value, then we're going to cancel all of these out, and we're going to be left with 2 is equal to B to the power of d. And just like we did previously, if I multiply or raise this to the exponent of 1 over d, these will cancel out, and I'm left with 2 to the 1 over d is equal to B. And that's basically the expression, because then afterwards we can plug it into our original when we're looking for our value of B. And 1 over d, not 1 over 2, sorry, that's confusing. So my original expression was A naught B to the power of t, but B, remember, is equal to 2 to the 1 over d to the power of t. And we can then rewrite this expression as A is equal to A naught, bring that 2 out, and we'll multiply these exponents, and that would be t over d. Now let's look at the last two examples. A patient feeling ill had a sample of bacteria taken from her throat, and the sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. Alright, so let's see what we have. We have our value of A. If we look at the formula above, we're given a formula that tells us that the amount at a certain time t is equal to the initial amount, and that initial amount is multiplied by some constant that's going to be raised to a power, a specific power that takes into account the doubling time, half, tripling, or half-lives. And then that is also raised to a power of time. So that's the function that we need to use here. So now we have to see what we actually have. Now we know that it contains 8,012 cells, so we know that A is equal to 8,012. A naught, what do we start with? Well, the sample contained 387 cells. What constant are we looking for? Well, what we need to determine is what's going on. Well, it's doubling. So our constant we're going to use is 2. And the time it took was 24 hours. And so we'll use 24 hours. And what we're looking for, though, is the doubling period. So we don't know what P is. So let's figure out what we do have by plugging, or what we need to find, which is the period, and let's figure out what that is by inserting what we do have. So 387, and we have the doubling period, which is 2, and we're raising that to 24 over P. Now 24 over P because I just combined these two exponents, so it became T over P. And now we can rearrange this. This can come 8,012 divided by 307 is equal to 2 to the power of 24 divided by P. And if I take the log of this, then what I'm going to be left with is log of 2 times 8,012 divided by 387 is equal to 24 divided by P. And then what we got to do in order to solve for P is divide 24, cross multiply here, right? So we're going to go P is equal to 24 divided by log 2 of 8,012 divided by 387. And P is going to be equal to 5.4897 or 5.5 hours. And the last one, we're using the exact same formula, but instead of my value of C being 2, my value of C is going to be 1/2. All right, and so this is one you can probably do on your own.